So my name is Boris, guys. I work for MongoDB. We're the database dudes. And I will talk now how we are working on distributed transactions. That's interesting because most people don't even know that MongoDB is ACID compliant. So the first thing, what you want to ask yourself, seriously? JSON, transactions, didn't the guys always say, we don't do that? Fair enough. Let's be honest, transactions are cool. It's great to have something where you can secure data in a way that if something should happen, it happens, and you can afterwards prove that it actually happened in a way that you wanted it to happen. But whoever built a transactional system in relational databases, and I come later to that part, relational databases are really, really crappy. And I did it for 30 years, so I'm allowed to say that. So if you do transactions bad, you can become a melted gummy bear in seconds. Yes, I choose that slide. And yes, if you ever smelt a melted gummy bear, then you understand it's something really naughty bad. So you want to try to avoid having smelly melted gummy bears. The key thing is, what can we do with transactions is very efficient, but it can be really, really wrong. So when we think about the standard use case, the most basic use case when we talk about transactions is we have two different things. We have invoices and we have balances on bank accounts. We have trade and we have the actual position in the account. You want to make sure you don't do one without the other. You always have multiple things you need to bring together into one envelope. And I compare this normally in a pile of paper. And I put a stapler on it, like bang, staple it together. That staple together is one set, and the staple holds it together, and the staple is called a transaction. That's very simple. There are other examples. Account creation is a good one. Think about you do online shopping. We all love it, I know. Only problem is somebody needs to pay the credit card end of the month. So when we do account creation, you go to a new site and it says, okay, you want to continue, order, you go to the order button, press, buy, pay all your stuff, credit confirmation, it says, create new user, because the system needs to be able to create a record where is the stuff you want to order shipped to. These are, again, situations where you need to make sure that certain things happen in a certain order of the system, otherwise you have to roll the whole thing back. And you need to make sure before you take the money, you are able to deliver the goods. Simple rules. These are things where you want to have transactions. But on the other side, besides talking about all the difficulties, they make things easier. The most important thing is when you have a pile, stapled, transaction, you don't need to think about intermediates. It's everything happens or nothing happens. That's this infamous thing you probably heard about, two-phase commit. It's a standard state for any transactional system. The better part is rollback and abortion are handled independently. The big problem is often without transactions, you need to think about, okay, did this update happen? If this is not happened, this one needs to be rolled back. You can write the whole logic yourself. But this is one of the things when you can ask yourself, do I want to write that logic? Or do I have to write the logic? And the right answer is, if I don't have to do it, I don't. And the third one is obviously point-in-time consistency. Classic example again, you have a warehouse file. You want to make sure if you have 5 pairs of shoes in stock and the dude wants to buy 1 pair and the next dude wants to buy 3 pair, the last one can buy maximum 1 pair. So you need a certain order of things happening and you need to always have one completed before the next one comes in. So all these kind of things about point-in-time consistency, the interim states and the abort handling, all these things are pretty critical. So when we take a look how this happens, it's really, really simple. First, we start a session. How's this called in relational? So we start a session. And then obviously we need to get a handle on our session to the data we want to work with. So in my example here, I have 2 collections. Collection is something like a table in MongoDB. And I have one called payable, the other one is called invoice. Not very intellectual, I know, but we stick to that example. Next thing is, I need to open up my bracket. I need to open up my transaction, where I'm saying, okay, let's put the following pages together. All this belongs into one stable. And in that part, I'm talking about already what is my read concern level and what's my write concern level. In a default, you don't need those, but in this example, I use them. Later, I will tell you how they work and what they are. Keep it in mind. You have different levels, how you can define what read behavior is happening, what write behavior is happening. Anybody knows how this is called in relational? Conditional reads, unconditional reads, conditional write, unconditional writes. Same thing, but in MongoDB, the data are much different handled. We have shards, we have replication, so we have a different level between these two, and we will talk about that one. Now comes actually, we try executing the transaction itself, updating our two columns. In the case of an error, we run the error handling, build an error handler, close the whole thing out. Now comes actually the writing, we commit, classical commit, transaction is closed, put the stabler to the pile of the paper, and last, we close the session. Not closing the session has what impact? Same as in relational, sessions stay open, handlers stay open, snapshots may stay open, things are not committed correctly, so the transaction is committed, but you have an open handle, you have an open cursor, you have too many open cursors laying around, the database gets sluggish. Now, there's a nicer way to write that one. This is the same thing in short. I can directly do a new API in MongoDB 4.2, and that is a little bit shorter. So, we talked about transaction guarantees. What's a transaction guarantee? Transaction guarantee means we execute something with the magic word asset, which is not related to any drugs. Anybody? Atomicity? Anybody else? ComSci people, I love it. So what are the typical things what we can do? Obviously, you saw the first one. We have multiple collections. We have two different collections, and we can build a transaction over that one. You saw as well the two collections can be in different databases. Obviously, we want to have transactions over multiple statements. We had two insert statements, two updates in the file. Obviously, we can do that one. We can have multiple documents, and now the new thing in MongoDB 4.2 is shards. So we have now a sharded database which can be geographical distributed. You have a node in Bratislava, one in New York, one in Tokyo. And now you need to synchronize transactions. That is where the art starts. I was responsible for the DB2 development at IBM. We were never able to build that, by the way. They didn't let us. It was too expensive. MongoDB, we built it. The whole effort around the transactions is a development which went over several years with huge investment of people. So that's a classical execution. What do? The transaction says, I want to update 3 documents. They are somewhere inside of a MongoDB engine. At this time, they are uncommitted write operations. Uncommitted means they are there. So if I'm inside of that transaction boundary, do execution of further statements, I would see the updated data. The other applications may not see it. Then I send the commit, which was the last command, and the data get committed, and everybody sees the data. So far, the standard technology, what is utilized on anything, what you do from relational. Everybody with me? Say yes. Good. Because if you have a problem with this one, then I'd rather repeat it. Otherwise, we have a really bad day. So what's a snapshot now? Snapshot is very simple. There are transactions running. Now the database has to run a snapshot. A snapshot over the database gives me a fixed point, normally session closed or things like that. Now more transactions coming, I pull another snapshot, and there's some rules around that one. But the snapshots are my fixed point where I can have borders between transactions, where I can borders between execution, and most important, I synchronize across a complete cluster data for the execution. Now comes Boris' little cookbook. And no laughing, I put it in a really nice form, so nobody gets really funny, and remember the gummy bears. And remember the title? With great power come great responsibilities. So if you want to become a melted gummy bear and you ignore these rules, That's your main point on that one. The key thing is all things you know about data modeling still apply with transaction or without transactions. The more you do certain things wrong by modeling things very distributed in very unpractical form across a large cluster, think every transaction has to go from Bratislava, Tokyo, and New York in the same environment instead of some data co-located, can be really negative for your health. Transactions should not be the most common operation, and that one I can only stress enough. Most applications, most cases, you do not have to create a transaction. Again, this joke about Spider-Man great power is actually true. In relational databases, you have a lot of very weird situations where you have a large number of different tables and you need to coordinate all the time. You will be very quickly in a situation that you need to do two-phase commit transactions. There's no way around it. For a MongoDB system, it's still the exotic case, and you saw the examples what I used. It's not the default. Single document operations, normally you don't need to do at all transactions. And don't forget to pass the session statement, session ID. You don't have a session ID, what happens? The statement gets executed locally, globally, outside of the transaction boundary. You have no control over it, and it may does a read operation and reads not the already before updated uncommitted writes, but is doing something in the middle out of nowhere, and the result is wrong data. And at that point, remember the gummy bears. Implementing retry logic, think about what happens if a transaction aborts. Do you want to have a retry, like retry 3-4 times with a sleep in between? Or do you want to have an abort and send back saying, sorry, shoes were not available, or things like that? Don't leave snapshots open. We heard about that one. Write conflicts. Yes, you are technically able to create write conflicts. Very simple. You have two transactions open trying to attack the same document. You have a write conflict. If you don't have a write, you don't have a conflict. Very simple. Reads don't generate write conflicts. That's why they're called reads, and the other things are called writes. Anybody ever heard about a read conflict before? No? I can tell you one. Yesterday, Trump's chief of staff had a read conflict with his boss. Just read CNN. That was a political joke. And make sure you plan for DDL, meaning what are you doing for backup, what are you doing for management, maintenance timeframes. If you have transactions open, transactions may block documents, documents block collections, and at that point, certain operations need to be thought about very, very clearly. How do you take care of those? This is my little menu to make a good food. I love my eggs on Sundays. Don't make the 2 eggs becoming 2 burnt gummy bears. Deal? So now let's look how MongoDB does actually distributed transactions workflows. We have majority writes. Billiard ball goes in, transaction goes to the primary node on the database. Hey, the primary says 2 of the secondaries got the information, and what are we doing? We are done. We're in business. We have a majority write executed. 3 out of 5 got the information. How the rest replicates afterwards, we don't care about. Now, there's one thing, no arbiters. Anybody here deals with arbiters in MongoDB? No? These were when you use only 2 nodes and trying to squeeze out a third node and try to be cheap, stupid stuff. Read up about it. It's a historic thing. Nobody should use arbiters. And with transactions, you can't use arbiters. You need 3, because why? Majority writes. With 2 nodes, you can't have a majority. And an arbiter cannot write. Ergo, 3 means minimum writing 2. In our example, we have 5, means majority is 3. Very, very simple, eh? We have participants in the transactions, and we have a coordinator. And this is very, very cool. The coordinator is the first partition, the first shard, which gets the information and initiates the transaction, and the other guys playing together with him. I call that, it's a quarterback in American football. So if you know this thing, there's this one guy standing behind and says, 45 blue, left, whatever, and then everybody executes that one. And this is exactly what the coordinator does. The coordinator brings together the execution of the transaction. So we're doing an insert. The query router MongoR takes the data and bang! Hey, this is my shard, that's where the transaction goes to. And the second one comes in on a different table, on a different chart. That's a participant. So now we have two uncommitted write operations in two different charts. Next level, commit. So what happens now? The coordinator needs to tell the other one, dude, hey, we're committing. Write it down. So what happens is majority write, the two primaries start replicating the data, and actually the single commit is executed over both nodes independently, both do the updates, and then finally replicate down to the third node. Very, very simple. Key thing to realize is shards are independent. You always have one coordinator, one. And the one is the one which gets the first set of data. Think again about the data modeling. If you afterwards want to talk a little bit more detail about it, this is the most difficult thing we do today. Everything afterwards is easy. So there's now one of those, oh my God, slides, marketing. No, this is not marketing. Where is this coming from? This is coming from writing your own retry logic, writing your own transactional cover-ups afterwards, your error handling, all that stuff. And whatever you write cannot be as optimized as something which is a layer lower, is handled right on the data level, and is actually able to do things where you have to go to much longer code paths. So at the end, this is not how smart you are or how smart the database is. This is all about code path length and code path execution. Very, very simple. The longer the code path is, the slower is your application. The more tests you have to run through manually, the more you need to execute. Keep this in mind. And obviously, the better performance results, the more you collocate, the less number of shards are involved, the easier is the execution. And guess what? This is not specific for MongoDB. That's not something special. This is a standard for any distributed database system, relational or else. Hierarchical, choose it. Collocated data can be executed faster. Very simple. Think about what was the first rule in my little menu? Think about data modeling. Very, very simple stuff. If you can't collocate and write to a single shard, try to be smart in that one. Read isolation. And I'm speeding up a little bit. I'm running out of time otherwise. We have read concerns and read isolation. Remember the two parameters we had, read concern, write concern. What are the things we have? Local, majority, snapshot, and linearizable. Whatever the last one is, ignore the last one. I don't even will talk about it. But the key thing is local, majority, snapshot are exactly what they say. Local read means you only go whatever is local and you just believe it. Complete unconditional read. It may be the latest, may not be the latest, but you really don't care. You take whatever is the next node and take the data out. Then comes majority. What does it mean? At that point, a commit may have happened. Now it's different. May or may not have happened, and the majority of nodes has an updated information already received, and I get the data back. That's kind of a semi-conditional. That doesn't exist in a classical relational database. And then you have the snapshot level, which is the hardest statement what you can have, where you say the transaction need to be snapshotted. Not only the transaction is committed, but the transaction need to be committed on a snapshot level across the whole cluster. That is the slowest state you can achieve, obviously, where you say it has to be in the system. When we talk about the last one, linearizable, whatever, that one we ignore. That means that things have to be sorted in a certain fashion. This is even slower. Ignore it. I don't even have an example for it for good reasons. Local makes sense. Majority makes sense. Snapshot makes sense. Now, anybody has an idea why majority does not need to coordinate across nodes? Because the router knows what is executed and can always check for majority write on the coordinator. The coordinator knows if it's written or not, and therefore can reply on the majority back. Not something very difficult to do. Very, very easy. So read isolation, what's the default? What you should use in a default environment is normally majority. You want to be faster and a little bit more fluffy, you go for local. You want to be really safe that everything is really down on the books, you go to snapshot. Makes sense, right? So we have 3 states instead of the 2 states on a typical relational database. And about the snapshot, so we talked about it. Across the database, every single of the transaction is committed, is in the books, is snapshotted, it goes through all. That's the highest level you can achieve. Where does this make sense? Give me anybody a good idea? Payments. Payments. You want to make sure the dude actually has money in the account. You do a transaction from Australia TransferWise. You're doing Australian dollars, Australia to Russian rubles. Let's choose something naughty. And you want to make sure that there's actually still money in the account and the guy did not start 3 different transactions 3 twice before and get 3 times paid with money which is not in the bank. So you want to make sure everything is snapshotted. You take the penalty of a slower execution of a transaction at a higher level of guarantee of delivery. Makes sense, no? Then local or majority, yeah, data are somewhere. Can be different snapshot levels and at different state. Now, locking. Locking is one of the things, when do we lock? When we write. Locks is write. So, for that one to have an effect and to have fun, we need obviously 2 transactions want to lock the same document. This is the same thing like in my days in university. There were 600 guys in the room and 3 girls to date. You have pretty much the idea. Transaction 1 blocks a document and writes. At that time, the document is locked and has a little marker and says, I belong to transaction 1. Now comes the second one and says, hey, got rejected, got thrown out because it could not get a write lock. So what happens to the transaction? Transaction is rejected, reports an error. You need to have a retry logic implemented, which says, okay, sleep 15, retry later. Typical example. It's completely rolled back and nothing happens. So now something else. Transaction goes in, document is locked. Now comes an operation. What's the difference between transaction and operation? An operation in MongoDB is the same statement like a transaction without a transaction bracket. Therefore, it's just a normal MongoDB update. And in this case, something cool happened. And now think again, oops, the guy talked before about I don't need always transactions because single documents are locked anyway at each state. So what happens now is the operation is actually not aborting, the operation is spin locking. So it waits and says, lock gun, is a lock gun, is a lock gun, is a lock gun, is a lock, until it's done. Except obviously there's a timeout parameter where you can say how long should it hang until the maximum timeout is reached. That timeout is default 60 seconds, but it makes sense to think about some application can take longer. What is a good example? Anybody book travel online? When you have long-running transactions where it takes really long time to do certain things remotely, think about address check, credit card execution, booking back to Amadeus for your flight. All that stuff can easily hit 60 seconds. So you want to make sure that you really look, if you get these weird behaviors on your app, that you may want to change the timeout for the retry on the operation. That's a tip. So, again, summary, very simple. Transaction abort, transaction blocks transaction. Transaction does not block operation, but transaction has to close before the operation can continue. Easy, huh? Now, read and writes, very simple. Transaction goes in the doc, blocks the doc, read. What happened? Why is it not blocked? Because it did open a transaction bracket, but it did not start a write operation. As long as no write operation is opened at that time, There is no log pulled. Think about the rule what we had, number 6. You need to have rights to have logs. So even if you open up a transaction, there is not an automatically dependency on logs. Very, very important. Now comes the second transaction which want to write, can still get in even if it doesn't block. Typical execution would be you do a lot of lookups up front, and only at the end of a transaction you do a single write operation very late in the game. The log time is in that part much shorter, even if the transaction bracket may be several seconds. Again, the example, think about the lookup for the address. You do first a lookup of the address, then you do the credit check, then you do whatever, and only at the last point you log the document and write down ticket booked, ticket status, issuing, zack, zack, updating the document. And then commit. Your log time is much, much shorter than the whole time over the whole transaction. Where do you know these behaviors from? From relational databases. Same thing. The only part is, for relational databases, a lot of people love to do something like, in the beginning first, update, counter, transaction number, or something like that. Or insert transaction number, insert new transaction number for financial transaction. What happens? Bang, there is a log. And why do they do that? Because they're scared about log conflicts and so on. So they try to lock the whole thing as good down as they can, with the understanding, if I have my logs all done, the probability that I get a log conflict is actually low, which is the most stupid statement you can make, because you have actually a higher log impact. As soon as you enhance the parallelism to the system, you don't need to be magic, you can do the math, right? Number of parallel threads doing logging divided by number of transaction records by number of hot spots in the database, and you have the probability to how fast this happen. Guess what? Modern system, 64 thread easily. Let's go to 2,000 threads, and you have 100%. It's not very hard to figuring out. So you want to try to avoid these kind of activities, because it makes your employer unhappy, your boss normally unhappy, and makes you a melted gummy bear. That was transactions and fast. Of course, now comes the advertising marketing section. Transaction larger than 16 megabyte. Before, you had to group the statements together in a statement group. By now, statements are completely independent. That's something nice. Can you do with anybody large transactions? In theory, yes, but it's really, really bad idea. You need to write sooner or later all that stuff into an ops log, and that's a serial operation. If you come to the brilliant idea to take 6 gigabyte movie files and run them as a single transaction to update them, this is not a good idea. Again, there was this purpose of the 16 megabyte limit at a while, and it is actually a good reason to stick to that one. That said, most transactions I'm dealing with are normally in the 4K range or lower. Because if you think about the data you're pushing through, financial data, things like that, 4K is actually a lot of stuff already. Name snapshot, think about the time, how things have to go through, what has to happen. You can, again, tune the time limits. Mutable shard key values is another one which comes in that point. You have no transactions. You're writing all this stuff in, but some transactions or the content of them gets older. So with mutable shard keys, I can slowly move data from ultra hot to lukewarm to ice cold onto my data lake without thinking about anything else, which is really, really nice as well for global data redistribution too. And the final comments, use latest drivers. In this picture now 4.2. I love it when people tell me, oh, that feature doesn't work. 2 people came today. That doesn't work, and then came out, do you use actually the client driver, which is fitting actually to the database version? The answer was no. So make sure you update your drivers, even if it's sometimes hard. I worked long enough with ISV software myself. Driver updates or any version updates are really highly appreciated by the project managers, meaning don't. But try to make sure you use the latest drivers. Try to remember, single shards are always faster than multiple shards. Remember the picture where we had to ship the stuff out with a quarterback? That is much, much, much slower. No more than 1,000 documents modified in a single transaction. I know where the product managers came up with that statement, but I full-heartedly agree, My answer would be actually something way lower than 1,000. There should be no sense in having 1,000. Imagine you do a database update with 1,000 rows on a database. Deadlock is guaranteed. No arbiters we talked about. Remember again the DDL part. Larger migrations, larger actions, whatever happen after the closing of the transaction snapshots. And there's a free class. Who of here in the room has used universitymongodb.com? Whoa. Who likes free stuff? Good. University.mongodb.com. Really awesome free classes. Really awesome free classes. Other thing, cloud.mongodb.com. Awesome free test cloud platform. Select free tier. No credit card needed. Nobody sells you an apartment. Nothing dark happens with it. We promise the only thing we have is your email because we need to attach your machine to your name somehow. But you can make nice little databases. There's sample data as well. Play around with this stuff. Figure out transactions. I really, really, really suggest using that one. If you're new to MongoDB and new to these kind of systems, universitymongodb.com, basic classes. I had the situation when I was at FIS and I started migrating applications over to MongoDB. My developers were, I know SQL Server, I don't want to do this stuff, I'm committed to Microsoft. So basically, there was this kind of the drones of the Borg consortium, and we put them to these classes. 2 days later, they were at the point that they actually listened to the stuff, tried it out, and were really, really good. At the end of the week, they had the first prototype running. So this is not marketing, this is practical experience for me as development leader. And at that point, I think I'm really good in my time today. So I behaved really, really well. So I'm open for questions. Yes, sir. Yes.
Let's say you have two transactions with a couple of statements in them. So the first one has a read, another read, and then write. The lock will be placed on the last statement. But let's say before this write lock happens, the other transaction writes the values which are read in the first two statements of the first transaction. Will this cause some, I don't know, deadlock or some transactions being aborted? Because it will look like the data that's been read in the first transaction will be changed before the write in the actual data.
Start with the first point. So the question was, we have an open transaction. We have some in the transaction picture. It's basically transaction A is read, 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 at the end a short write. Now the same transaction runs on a different thread on a different app server against hitting the same record and is right now in the write phase. So these are exactly the read concern question, where you're saying, wait, do I need to have a snapshot? Do I want to make sure I go after the last snapshot? Do I go because the write on the other machine, obviously in your example, have happened, but is not committed yet? Correct? Otherwise it's boring. When it's committed, they get the latest one. If it's not committed, then we have this limbo situation, what you talk about, right?
Yeah, so let's consider there with the snapshot one.
Yeah, in the snapshot one, it's very easy. The transaction, if the other transaction, the one which is just writing right now, will not be considered, it will be completely side-passed because the transaction will take the last snapshot level, looks after those data, and only those ones which does not include the open non-committed one at this point. The only way how we would get that is, for example, when we do a majority, now is it read concern majority? Then it has to be written and committed already on majority. And if the majority is committed, that means 2 out of 3 nodes have them already, it would get the read committed. So I have to look up to a dude right now there, Felix, at which time the commit would come in. The commit needs to be in, right, on the majority. No, it doesn't matter. It's basically, his part is that we have overlapping transactions. So there are multiple rules now. That's what he's referring to. An update would be different behavior than an insert, for example. So we can, I don't want to kill this now. I'm just leaving this a little bit out right now. We can do it afterwards, but bottom line is the rules, depending on what rules you define for read concern, write concern, depending on the rules, you have different results in the execution. That is correct. And the most basic one is in the case of snapshot. If you have a lot of those concerns, you would go snapshot to ensure you have always a clean execution path. Other questions? It was a good question, by the way. Other ones? The dude in the red shirt again.
Do you have deadlocks in MongoDB?
Can you generate deadlocks is basic questions.
Yeah.
Yes, you can, but it's much harder. Why? In normal deadlock situations for relational databases, you have a large number of tables affected, and the more tables are getting involved into a lock, the more locks you pull, the more probability you have that transactions with different execution interlock each other and you get circular locking. Because deadlocks always means circular interactions. Now, with MongoDB, we talk about documents. Normally, we have actually much smaller number of documents involved, which contain the data already, so the probability for deadlocks becomes actually much, much slower. Have I seen so far a MongoDB deadlock? The answer is no. Is there a theoretical capability edge case to generate deadlocks? The answer is yes, very clearly. There's no system where you have locks where you cannot generate deadlocks. That's kind of a contradiction. That's what a lock means. So you would need to generate a circular kind of pattern, locking behavior with reads, writes, intertwined in a way. I'm sure mathematically you can generate an edge case.
Is there some behavior on MongoDB when there is this theoretical case? For example, in relational databases, they kill.
There is log escalation as well, obviously involved. Absolutely. So, and if we have more, oh, there is another gentleman not in a red shirt.
Are you breaking with this?
One second.
This stuff, are you breaking cap theorem or not?
Again, with the speaker, so it's easier to understand.
I'm asking if we are with all of these transactions, what you said today, if we are breaking cap theorem or not.
No, we don't.
Okay, some next questions?
Nobody? Cool. I'm still around here, so I'm happy to answer one-on-one questions. I know it's always hard in a group like this to stand up, especially if there's a gentleman in a red shirt in the room who want to have more questions. Yes, you might. I have as well some stickers here. So if anybody wants to have stickers for the laptops. And otherwise, I think we're really good in time today. I thank you guys that you spent the last session of the day with us. And thank you very much.
Okay.